Okay, as usual, what I'd like you to do first off is identify what are you trying to find. So it says how much potential energy does it have. And that means from our equation, BE equal M times G times H, we should be able to identify those other three things, which in this one is also straightforward. Mass, that's obviously the 750 kilograms. G is always going to be our old friend, 9.8 meters per second or meters per second squared. And H is the height that it's at, and this is given as 1 meter. And to find potential energy, all we have to do is to multiply them. Yes?
7,350?
Joules, you got it. Easy peasy. We'll get a little bit of a feel for how much a joule is, but this kind of unit, in my experience, is pretty hard to really know what a joule is. If we want to, in comparison, a topic that we'll talk about later, mostly with having to do with electricity, is power. We use those all the time, like it's in watts. So a light bulb is often 60 watts. What that means is that's 60 joules every second. So 7,350 joules is quite a lot, especially when you compare that to say how long could this energy light up a bulb, so to speak. But it is pretty tough to actually say. Straightforward though, right? Questions? Okay, let's try the next one. What are we looking at here? Hoover Dam. Has anybody been there? It's pretty cool. Not only is it mechanically really cool, and you can sometimes get some tours down to see the turbines and things in it, just walking along it is really cool. And one thing I appreciated is the architecture. They actually made it look neat. It's not just a utilitarian thing. It's actually quite stylish too. But Hoover Dam, what does it do? How does it produce energy? Okay, so what does it do with the water in the turbine? You're right, you've got the first part. How does a hydroelectric dam create energy? What does it do with the water?
The water lights a turbine, blender sort of. And it pushes it, and it's like doing this sort of motion, and spinning it, and the spinning creates electricity, because when you shake things, creates energy.
Well, you're right with the first part. So the water is making the turbine spin. It's like a fan working in reverse. Instead of blowing air, if you blow on it, it's like a windmill. So it's essentially an underwater windmill. And we'll learn more about how electricity is produced later on, but it's turning some magnets inside coils of wire, and that moves the electrons around. And so that's transferring energy from this water into a different form, electrical energy. It's doing work. Anyone know why you need to have this giant wall here? I mean, obviously to stop the water, but why do you have to stop the water? There are, but this was just a river. You can see the river down below. It would have still been a river, and it would not have had all this water back behind it in Lake Mead without the dam. So it wasn't enough water to put those people in danger. The key here is potential energy. Because if you stop the flow of this water and fill it up, it is, and I've got the number, I can't remember it, it is 230 or something meters higher than it would have been without that. That's a lot of potential energy that it builds up. And we're going to convert that potential energy the water has into electrical energy as it goes from this level down to that level. So here is the question. Water falls 290, I stand corrected, meters as it drains from Lake Mead to the Colorado River below. Every second, about 90,000 liters of water pass through those turbines. My question is, how much gravitational potential energy can be turned into electrical energy by the turbines each second? So we're looking at 90,000 liters going that far. So this one, like the last one, we're still looking for potential energy. The per second stuff, just sort of, we don't even consider that. We're just looking for potential energy, and the way it's worded, we're looking for it every second. So we don't have to worry about the 90,000 liters of water per second or the joules per second. But we do have to say, we need the same three things as the last time, M, G, and H. G is always going to be the same, 9.8 meters per second squared. H here, what is the height that we're considering? 290 meters, because that's how much it's changing. So we're taking that amount of height out of it, in essence, and seeing what's the difference between this point and this point. There's our height. What about our mass? We're given it in liters. How do you convert from a liter to a kilogram? Somebody's got to have an idea, because I know we talked about it early in the year. Good. 1 liter of water does have a mass of 1 kilogram. That's actually how a kilogram was defined. That's the relation. It's a really handy relationship in the metric system. A liter of water, not of anything else, but of water, has a mass of a kilogram. So if we've got 90,000 liters of water, how many kilograms do we have?
90,000 kilograms?
Yes. Same amount, which is just an easy conversion. Now we can multiply those. The mass of 90,000 kilograms times G times the height difference of 290 meters. And now with that small correction, what did you get at?
255,780,000
joules. Now this is probably the peak, or that's really, really high, and that's every second. So that would be, we turn that, we have kilo here, this is mega, so that'd be like a 256 megawatt generator. I don't remember if that's really reasonable or if it's a bit high, but it's going to produce a lot of power regardless. I think we have one more example. We're on to our next topic. Hooray. But the only other thing I might potentially ask you about here is, and we'll get to that as we practice, is if we already know the energy of something, say it's 60 joules, and we know its mass, we should be able to rearrange this and figure out how high it must be. And that can be useful as and I think we might have an example after the kinetic energy, as we're starting to convert one energy to another. Say, if you put in 60 joules, how high could you lift something? But we'll get to that in a little bit. Second topic is on kinetic energy. Who remembers what kinetic energy is? Moving energy. So when something's in motion, it has kinetic energy. It's the energy an object has due to its motion. So anything that involves moving things is a type of kinetic energy. We're going to do sort of the basic definition of what kinetic energy means. we have another formula. We're going to get, I think, 3 formulas this chapter. We've seen the one. Here's our example, so it's turning into that. There is our kinetic energy formula. 1/2 times m times v squared. That KE, kinetic energy, just like every other form of energy we're going to talk about, we're going to measure in joules, because that allows us to easily switch from one form to another. M, as usual, is mass, and just as usual, we're going to measure it in kilograms in physics whenever we measure mass. What about that V? Velocity or speed, and we square that. Velocity in meters per second. Technically the speed, it's speed because the direction isn't important, but whichever way you want to remember it. Our first example here is straightforward again. It asks specifically for how much kinetic energy does it have. We have to find that, meaning from our formula, 1/2 mv squared, we have to figure out or list the mass and the speed or velocity. Mass is given as 0.15 kilograms. Speed is given as 35 meters per second. And now we just put them in. 1/2 times 0.15 kilograms times, and here's the only trick that you've got to remember for this. You're only squaring the 35 meters per second. So if you've got a graphing calculator, like one of the TIs, no problem, you just put the square sign after it. If it's somewhat different, play around to make sure that you're using the calculator the way it's intended, because it is possible, unlikely but possible, that if you multiply 0.5 times 0.15 times 35 and then hit your square button, it might decide to square all of it depending on how the calculator is set up. So just do a little bit of experiment. If you've got a TI one, then I'm just going to hit the x squared button there and it squares just the 35. We get about 92 joules. So take a moment, if you've got your calculator handy, check right now to make sure that if you multiply that out, you get 91.87. I believe then the energy conservation is involved with these. We're going to do this one next. This is the first step that we're going to look at. So now, let's imagine we have a 750 kilogram car that has 9,400 joules of kinetic energy. How fast is it going? Okay, this one, it says how fast is it going, so we must want to find the speed. We're given a mass, 750 kilograms. We're given the kinetic energy of 9,400 joules. But we are left to figure out how to find the velocity from that. So we'll start with our base formula. We need to get V alone, not V squared even, just V alone. What do you think? What should we do first?
Can we divide V squared?
If we divide V squared, what would we have on the left?
V or K divided by V squared.
And then we have V squared on the bottom. So yes, we can, but we shouldn't. Let's just get everything else away from V squared. We'll leave it on the right. I don't care what side it's on. We'll just get everything else away. Divide both sides by 1/2 m squared. So if we do that, cancels out the 1/2, cancels out the m. So we have Ke over 1/2 m. Another way to write that is if you divide by 1/2, it's like multiplying by 2. So that would also be 2 Ke over m. And that's equal to what's left, V squared. So now I'm going to work with this second part, but they are equivalent. How do we get just V? What's the opposite of a square? And I don't mean circle, yeah. Square root. So you gotta take the square root of both of these sides. Like so. That will give us just V. We don't have to worry about the plus or minus root in this case. Is equal to 2 KE over M. I'm running out of room here. A very important thing to remember here is order of operations on a calculator. Again, if you've got one of the TI calculators, when I hit the square root button, you notice it puts a parenthesis after that. You don't have one that has that. I would suggest multiplying or dividing this stuff out first, getting it to its end result, then taking the square root. But I'm going to have to put over here. With this kind of calculator, you don't have to do that. So I'm going to put 2 times 9,400 over the mass of 750 kilograms. And then because this calculator uses parentheses, I can just put those in and not worry about the order. And I get 5. 5.007. What units? Joules. It's of speed, right? So we'd expect meters per second. Let's take a look at what we've got down there. Joules are actually that kilogram times meter squared per second squared. We're dividing that by kilograms, so that just gets rid of the kilograms part. We still got meters squared per second squared, but we're taking the square root, and that leaves only meters per second. Take a moment right now with your calculator to put this part in, and make sure you get 5 out, so you see the order of operations. Right, now we're going to start looking at changing energy from one form into another. We're going to start with a baseball held 20 meters above the ground and figure out how much potential energy does it have. So we know its mass. We know G, 9.8 meters per second squared, and we know its height starts out at 20 meters. So compared to the ground, here's how much potential energy it will have. And this will help us figure out some other things about it as it falls. Joules. Okay, now we're going to use that in a couple other problems that follow. Second question, how much kinetic energy does it have while it's held? We know its mass still, 0.15 kilograms. What's its velocity while held? How fast is it moving? No, it's not a trick question.
0?
It's 0. It's not moving, right? So how much kinetic energy does it have if it's being held? 1/2 times the mass times 0 squared gives us 0. So it has 0 joules. And I bring this up just to make the starting point we had. How much did we have before I erased it?
29.4. 29.4 joules.
29.4 joules of potential energy up above, and then only 0 joules of kinetic energy. This energy can change from one form to another, but this is all the energy it has. It's never going to have more than 29.4 joules, even though as it falls, it'll be losing potential and gaining kinetic. They're still going to add up to that 29.4 joules. Okay, so the next one asks about that after it starts moving. How much potential energy does it have as it strikes the ground? So in your notes, just add that that second sentence. As it hits the ground, how much potential energy does it have? And as usual, we're going to look at just as it's hitting the ground rather than after it's hit the ground. Anybody have any quick ideas? No shortcuts, let's do it. We want to find potential energy, we know the mass, 0.15 kilograms, we know G. What is the height as it hits the ground?
20 meters.
Is 0 as it's hitting the ground. It started at 20 meters, but now the point we're looking at is as it strikes the ground, so 0 meters. So how much potential energy does it have? 0. 0 joules. Doesn't that break the law of conservation of energy? Didn't it just lose 29.4 joules of energy? I'm glad you're shaking your head. You can't break the law of conservation of energy. So what gives them? Jeremy? It's transferred somewhere else. Where do you think it's been transferred to?
Kinetic energy?
Kinetic energy. That's what happens as something falls. It's got a lot of potential initially, and it could have kinetic energy. If it were moving up here, it could have both. But as it falls, it's losing that potential energy, but gaining a similar amount of kinetic energy. So let me clear that. Question is, how much kinetic energy does it have as it strikes the ground? That doesn't give us a lot of information, does it?
No.
Obviously we want kinetic energy, but we have a mass, but we don't have a speed. Is it moving?
Yes.
Somebody whispered it has 0, but if this is as, not after it strikes, but just as it's striking the ground. If it's moving, does it have 0 kinetic energy? Must have a velocity, so it must have kinetic energy. Question is, where did that kinetic energy come from? Why does it now have kinetic energy? Jeremy, you guys together just answered that a moment ago. Why does it now have kinetic energy? Because it transferred energy from potential. It no longer has potential energy. We said it transferred into kinetic. So how much kinetic energy must it now have based on our previous problems? 29.4 joules. Right? We don't even have to calculate that in this situation. We don't need to know the speed. All of this potential energy that it had, 29.4 joules, it still has that energy, but it has none left in potential energy, so it must be in kinetic. Now the last question is, we can use this to learn more information than we used to be able to do. How fast is it going as it strikes the ground? Okay, like example a couple times ago, we know the kinetic energy from our last problem is 29.4 kilograms. We know the mass, 0.15 kilograms, put it in parentheses. And we want to know the speed. So we already went through and solved for speed, and we found that if we rearrange the kinetic energy formula, it should be equal to the square root of 2 times the kinetic energy over the mass. So we can plug in values for that. 2 times our 29.4 joules over our mass of 0.15 kilograms. And then take the square root of that. Thank you. Yep.
Answer?
Yep.
20 meters.
That one? Maybe. It seems a little high, but
Well,
yeah.
I got-
I'm gonna double check, but you may well be right.
Yeah, I got 19.8. Do we put
Okay.
that?
This should be close enough.
Okay.
Yep, 19.8, roughly 20. Whenever you've got a computer-based problem, it would calculate out that 19.79 whatever. But then there's a window, a 3% window around it, so plus or minus 3%, as long as you're within that. And this little bit of rounding would certainly be fine.
Okay.
So converting from one type of energy to another.